is,
See if anyone can hear you.
if you guys can hear me, hello. I'm going to just go ahead and quickly go over the things that I mentioned in the beginning.
No one can hear you throughout the whole beginning part.
Okay, so I'm just going to restart. We had a bit of a technical glitch. So again, welcome back and thanks for joining us in this episode of Virtual MOSI. My name's Jose, and today we're going to talk a little bit more on gravity. So gravity is actually the force that kept all those planets in orbit, and if you haven't seen that video that we posted yesterday, we definitely encourage you to do that. We had a lot of fun putting that together for you guys, and it was pretty awesome. So today I want to dive a little bit deeper and take a look at kind of what kept everything behaving the way it did, what kept the planets going around the sun, and things like that, okay? So let's get started. I already gave away the answer. I said it was gravity, and I'm going to talk a little bit more about this by using this ball. Right now, if I hold up this ball, it's actually experiencing a gravitational pull. And we experience a gravitational pull too, it's just that we don't often think about it. Now, the only reason why this ball is not falling is because my hand is counteracting that gravitational pull. However, if I were to let go and open my hand, you would see that the ball falls straight down. Now again, this is true because the Earth is a very massive object. And you might think that only very massive objects have gravity. But it turns out that every object in the universe that has mass has gravity. So yes, that means that even I, even you, have a gravitational pull, even a paperclip. So anything with mass has gravity. And I'll demonstrate what that means in a little bit. And in order for us to do that, we're going to use this pretty nifty piece of technology here, which we like to call the fabric of space. Now, this was actually provided to us by the NICE network. NICE stands for the National Informal STEM Education Network. And essentially, their mission is to provide educators with all of the right tools and components that help the community better understand science and different topics. So let's dive right into the activity here, and let's use this table. Now, we call this the fabric of space, right? And as you can see right now, we're representing space as this flat piece of cloth. So you can think of it as kind of a two-dimensional thing, but we of course know that space is three-dimensional right now. And I'm going to use this ball to demonstrate that the fastest way for the ball to travel through space is in a straight line. Okay, that's going to be important in a little bit. The fastest way to travel, of course, for light and things like that, will be in a straight line. If I place this very light ping pong ball at the center, we can look really closely, but there's barely any curvature around it. Now, I'm going to use a much heavier object here, this really heavy weight, and notice what happens when I place the weight at the center of the fabric. Notice how this object, which has much more mass than the ping pong ball, actually bends and wraps the curvature of space around it. And notice how the angle becomes steeper the closer you get to the object itself. Now, we're going to visualize this by thinking of the Earth-Moon system, because we know, of course, that the moon orbits around the Earth. And what better way to demonstrate that than using that ball that I had at the very beginning. So this is the moon, of course, and I want you to take a close look at what happens when the moon goes around, oops, oh, look at that, when the moon goes around the Earth. Notice the moon is trying to follow that nice straight line that we talked about earlier. It just happens to now be curved. So let me try that again. I'm going to throw the moon in a nice straight line. Try that one more time. In a nice straight line, and it's following the actual curvature of space. Technically, it's still traveling in a straight line. It's just that space itself is bent and warped and curved. Now, I'm going to take this time here to actually encourage you guys to ask some questions in the comments, right? So we have some of our staff members reading through the comments. As soon as questions pop up, they're going to let me know, and then we'll go ahead and give you guys an answer. And then we also will have a couple minutes set aside at the end so that we can better address those questions. So if any questions come up throughout the video or something that just, I never thought about this way. Go ahead and let us know in the comments down below, and then we'll give you a shout out, all right? So let's go back to the activity here. We saw that the moon orbits the Earth, and again, it's because it's following the curvature of space-time. Now, let's take this a little bit further. Let's actually swap out the moon for the Earth, because we know that the Earth orbits around the sun. So now this heavy weight will represent the sun, and we're going to take the Earth here and notice how it follows that exact same path. Now, the keen observers among you will realize that the planets are not following perfectly circular orbits. In fact, if you look really closely, as the Earth and the other planets move, they actually trace out kind of an elliptical orbit. That means that instead of the orbit being a lovely circle, it's kind of like a squished circle, right? So it draws out an ellipse. And that's actually one of Kepler's laws of planetary motion. Now, who in the world is Kepler? He was actually an astronomer way back in the day, and his work led to us better understanding the universe and how the planets move, and it even led Sir Isaac Newton to further develop his theory on gravity. So it's actually a really important person. But now, let's switch gears a little bit. We'll still keep this as the sun, and now let's think back to that planetary dance that we performed for you guys yesterday. So going back to that planetary dance, we had a few things going on. I'm going to use these marbles here to represent the planets, and I want you to notice what happens when the marbles get closer to the center of the mass here. Now, I'm going to probably have to do this a couple of times, but you'll find that as they're traveling along the outer rim of the solar system, if you will, the planets actually move considerably slower than as they travel around the inner portion. Why is that, you might think? Well, let's think back to the very beginning. I mentioned that the closer you get to the center of mass, the more space-time actually curves and warps around it. And that holds true for every object. That's why if you're trying to go into orbit around the Earth, you typically don't want to go too far away because, well, then the gravitational field of the Earth isn't actually affecting you and you just drift off into space. So this is something that we've experienced. And of course, the reverse also applies. If we have an object that's far more massive, say something like a black hole, then this funnel, this so-called gravity well, would actually be so steep that nothing traveling around it would be able to escape. So black holes are called black holes because not even light can escape the strong gravitational pull from the center. So the big takeaway from that is that massive objects warp space-time around them really like a lot, whereas not as massive objects also warp space-time, but not nearly as much. Another takeaway from that is that as the marbles get closer to the planet, they have to spin a lot faster to keep themselves from going in. You also realize that these marbles are slowing down. And that's actually because, believe it or not, there's a lot of friction in this system between the marbles and between the fabric of space-time. But out in space, there's really not that much friction to slow things down. So all of these orbits and dances can, of course, take place for millions, even billions of years. Now, we're going to bring you into the activity and take a look really closely. I'm now using a heavier object, a steel ball, and I'm using this to represent a larger, more massive planet. Because remember, the more mass you have, the more you warp space-time around you. So this massive planet is kind of a medium-sized planet compared to this large star here. And I want you to keep a close eye on the large star and notice what happens as the planet itself begins to orbit that star. If you look really closely, you'll actually see how the planet tugs on the star. Let's try that one more time. So the planet will orbit around the star, and as it gets closer and closer, the effect becomes more pronounced, but you'll find that it actually will tug on the star, cause it to wiggle around a little bit, and believe it or not, that's actually a technique that NASA scientists use to detect new planets. So this is one of the techniques that NASA scientists use to detect planets, what we call exoplanets, because it's really difficult to actually locate a planet by using visual light. By using visual telescopes, it's really hard. They're very, very faint and very small compared to stars. But because a planet can actually cause the star to wiggle, if we analyze the wiggle, the movement of stars, we can then extrapolate that there's planets around it. So that's really cool, and that's something that has led to the discovery of hundreds of planets to date. So that's really, really neat. And now let's talk about orbits and how they actually work. So here we've got a lovely representation, of course, of the Earth. This was drawn by my colleague Catherine, so shout out to Catherine. And we've got the Earth here, and we've got the Moon, which, as we know, is Earth's natural satellite. Now, in order for orbits to actually work, we have to understand the forces that are kind of happening behind the scenes here. So at every moment of every day, there's a force that is trying to get the Moon to fall down to Earth. Anyone want to take a guess as to what that force is? That's right, it's the same thing that if you jump up, it makes you come back down. We're talking about gravity. So gravity is always pulling on the Moon, always trying to get it to the center of mass. Why is it not the other way? Technically it is, it's just very, very minute, so the Moon doesn't even feel it. But in order for the Moon to actually stay up in space, well, it needs to move, essentially needs to have a velocity in a direction in order to move around the Earth. So it's moving at a rate that's a little bit faster than the rate that the Earth is actually tugging on it. So the Moon is moving sideways. It always wants to move sideways, but the Earth won't let it. It's tugging at it. So what happens is the next version of the diagram, which we'll see here, this is my version of the Moon, you'll find that the Earth is still tugging on the Moon, trying to get it to go back down to the Earth, and the Moon doesn't want to do that. It wants to keep going its own way. So then we analyze the Moon's new position, and you realize that this process repeats itself, and it keeps going and going and going, and ultimately you end up with what we, of course, refer to as an orbit. So if we extrapolate the data from here, you would find that the Moon continues to orbit around the Earth. And satellites that we launch to space, of course, have to keep doing this. Now the question is, what happens if a satellite goes too fast? Well, if it goes too fast, then it actually escapes the gravitational pull or the gravitational well of the Earth. So it actually can be lost to space forever. And then what happens if the opposite holds true? What if the satellite's not going fast enough? Well, gravity takes over, and the satellite would fall and burn up in the atmosphere. So that's actually some of the things that can happen, of course, as we go around space. Now, at this time, I'll go ahead and open up the floor to any questions you might have. Have there been any questions so far?
We have a comment from Arjun who said,
Ooh, yes.
"Whoa, this is heavy, Doc."
Oh, I dig the pun. Thank you, thank you. So hopefully you guys have enjoyed the video so far. Again, if you have questions, feel free to type them up in the comments. We'll be checking those comments. I know that school is kind of back in session, virtually, of course. But we'll check those out and get back to you guys. So once again, my name's Jose. I hope you've enjoyed this brief demonstration on gravity and that it explains a little bit why the planets behave the way they did, why they move slower the farther out they are from the center of the solar system. Again, hope you will stay safe. I hope you'll stay curious and keep discovering. Have a good day, guys.